Welcome to an exploration of life cycle assessment, a critical tool in the realm of green chemistry. Understanding this concept is fundamental for anyone aspiring to contribute to a more sustainable future. It provides a comprehensive framework for evaluating the environmental impact of products and processes. Life cycle assessment, or LCA, offers a holistic perspective, setting it apart from traditional environmental evaluations. It meticulously covers a product or process throughout its entire lifespan. This means considering every single step, from the initial raw material extraction to its final disposal or recycling. LCA employs what is known as a cradle-to-grave perspective. This approach ensures that no stage of a product's existence is overlooked. It is crucial for identifying hidden environmental burdens that might otherwise go unnoticed. By revealing these impacts, LCA actively promotes more sustainable practices across industries. The life cycle assessment methodology is systematically divided into 4 interconnected phases. Each phase builds upon the previous one, contributing to a thorough and robust analysis. These phases are goal and scope definition, inventory analysis, impact assessment, and interpretation. The first phase, goal and scope definition, is foundational to any LCA study. It clearly defines the objectives of the assessment. This initial step ensures that the study remains focused and relevant to its intended purpose. Without a clear goal, the subsequent analysis can become unfocused. This phase also establishes the system boundaries for the study. These boundaries determine precisely which processes and stages are included within the assessment. Defining these limits is essential for managing the complexity of the analysis and ensuring its practicality. It sets the stage for a focused and relevant investigation. Following the definition of goals and scope, the inventory analysis phase commences. This involves collecting detailed data on all inputs and outputs associated with the product or process being studied. It is a data-intensive phase that forms the backbone of the entire LCA. Data collection begins with raw material extraction. This includes understanding where materials come from and the environmental costs associated with their procurement. Every resource input is meticulously accounted for during this stage. The analysis then moves into the manufacturing processes. This involves gathering information on energy consumption, water usage, and any chemicals utilized during production. Every step in the transformation of raw materials into a finished product is documented. Transportation is another key element within inventory analysis. The environmental impact of moving raw materials to manufacturing sites and finished products to consumers is carefully considered. Logistics play a significant role in a product's overall footprint. The product's use phase also falls under scrutiny. This includes energy consumed during operation, maintenance requirements, and any emissions generated while the product is in use. For many products, the use phase can represent a substantial portion of their total environmental impact. Finally, end-of-life management is assessed. This covers disposal methods, potential for recycling, and any recovery processes. Understanding how a product is handled after its useful life is crucial for a complete cradle-to-grave picture. Throughout this phase, data is gathered on various forms of resource consumption. This includes energy, water, and all types of materials used. Quantifying these inputs provides a clear picture of resource dependency. Simultaneously, data is collected on emissions to air and water. This includes greenhouse gases, pollutants, and any other substances released into the environment. Understanding these outputs is vital for assessing potential harm. The generation of solid waste is also meticulously recorded. This encompasses waste from manufacturing, packaging, and end-of-life disposal. Minimizing waste is a core principle of sustainability, and LCA helps identify opportunities for reduction. Once the inventory data is compiled, the impact assessment phase begins. This phase translates the raw inventory data into meaningful environmental impact categories. It moves beyond simple quantities to evaluate potential effects. This assessment evaluates potential effects on various environmental aspects. It helps to understand the broader implications of the collected inputs and outputs. This is where the environmental significance of the data becomes apparent. Examples of impact categories include climate change, which quantifies greenhouse gas emissions. Ozone depletion, acidification, and eutrophication are also common categories. Human toxicity and ecotoxicity are assessed to understand potential harm to living organisms. Characterization factors are utilized to quantify contributions to these impact categories. These factors convert inventory data into a common unit for each impact. This allows for a standardized comparison of different environmental effects. The final phase of LCA is interpretation. This critical stage involves analyzing the results from all previous phases. It is where conclusions are drawn and actionable recommendations are formulated. This phase brings the entire assessment together. A key outcome of interpretation is identifying hotspots. These are stages within the product's life cycle that have the most significant environmental impacts. Pinpointing these areas allows for targeted interventions and improvements. The interpretation phase also explores opportunities for improvement. This might involve redesigning the product to use fewer materials or different components. Process optimization can lead to more efficient and less polluting manufacturing. Material selection is another area for improvement identified through interpretation. Choosing less impactful raw materials can significantly reduce a product's overall footprint. The insights gained here are invaluable for sustainable innovation. Life cycle assessment plays an absolutely vital role in the field of green chemistry. It guides the development and implementation of sustainable chemical products and processes. LCA provides the empirical data needed to make informed decisions. It offers a quantitative assessment of environmental impacts, moving beyond qualitative assumptions. This scientific rigor is essential for demonstrating true environmental benefits. It provides a measurable basis for sustainability claims. LCA helps chemists and engineers make informed decisions across several critical areas. These decisions are fundamental to designing products and processes that are inherently more sustainable. It empowers practitioners with data-driven insights. Regarding material selection, LCA helps identify less hazardous and more sustainable raw materials. It encourages the use of renewable resources and materials with lower embodied energy. This proactive approach minimizes environmental harm from the outset. In process optimization, LCA guides the design of efficient and environmentally friendly manufacturing processes. It highlights opportunities to reduce energy consumption, minimize waste, and prevent pollution. This leads to cleaner production methods. For product design, LCA encourages the creation of durable, recyclable products with lower environmental footprints. It promotes designs that facilitate disassembly and material recovery. This extends product life and reduces waste. In waste management, LCA aids in implementing strategies for reducing waste and promoting recycling and reuse. It helps evaluate the environmental benefits of different end-of-life scenarios. This closes the loop on material flows. LCA empowers green chemistry practitioners to move beyond mere pollution reduction. It shifts the focus from simply cleaning up messes to preventing them in the first place. This proactive stance is central to the philosophy of green chemistry. Ultimately, LCA facilitates the design of products and processes that minimize overall environmental impact. It provides the tools to systematically evaluate and improve environmental performance. This comprehensive approach is indispensable. By integrating life cycle assessment into their work, chemists and engineers contribute significantly to a more sustainable future. It is a powerful methodology for making informed choices that benefit both the environment and society. Understanding LCA is a cornerstone of modern environmental stewardship.